Homework last night, guys, two sets of it, 13.1, page 647. We had a number of questions on that page. We also had a couple of worksheets. We'll take a look at page 647 first. Any issues with 1 to 2, 5, or 7 to 14 on page 647, please? Any issues with those questions? Yep. 5. Yeah, I got 5. 10. 5 and 10. Any others besides 5 and 10? 7. 5, 7, 10. Going once, going twice. All right. 9. Okay, 5, 7, 9, 10. All right. Let's take a look at number 5 first. It says, explain how the observations made by Hertz support the electromagnetic theories of Maxwell. Let's look at the electromagnetic theories of Maxwell first. Maxwell said that accelerating charged particles generate electromagnetic radiation. He also said that electromagnetic radiation consists of changing electric fields and changing magnetic fields. Electric fields that cause the magnetic fields and magnetic fields that cause the electric fields. So that's essentially the theory. Now, how do Hertz's observations support Maxwell's theory of electromagnetism? Essentially, we say that, look, if there's electromagnetic radiation detected at the antenna, okay, then the electromagnetic radiation must consist of a changing electric and a changing magnetic field. Otherwise, you wouldn't get a current produced in the antenna. Okay, that's how we're detecting EM radiation in the antenna. There's a current produced in it. Well, you're not going to get a current produced in it if you don't have that changing electric and magnetic field. So it's got to be what Maxwell said it was, the changing electric and magnetic field, to get the current produced in the antenna. So number one, there is a current produced in the antenna, therefore there is a changing electric and magnetic field, just like Maxwell said there was. Now, where did that changing electric and magnetic field come from? Well, before we flipped on the switch, or before Hertz flipped on the switch, there was nothing. He flips on the switch, there's something. There's electromagnetic radiation detected. So the only difference between before he flipped on the switch and after he flipped on the switch is the presence of this electron jumping the gap. Okay? This presence of this accelerating electron, which is the other part of Maxwell's theory. Accelerating electrons or accelerating charged particles generate EMR. If there was EMR produced when we had accelerating charges, and there wasn't EMR produced when we didn't have accelerating charges, then accelerating charges must produce EMR. So the two observations, the two parts of Maxwell's theory, accelerating charges produce EMR, and EMR consists of changing electric and magnetic fields that produce each other and become self-sustaining that way. Those are both verified or both supported by Hertz's observations. Does that make sense? And you just got to summarize that in a couple sentences as opposed to a couple paragraphs. Next one we need to go over was number 7. Why is the process of changing critical to the production of EMR? Why is the process of changing critical to the production of EMR? Yeah, go ahead, Josh. Okay, that's actually not what I was looking at, but that's a good answer. Okay, you were kind of interpreting the question slightly differently than I was, and that's good for your interpretation. Okay, Josh said that the speed of the electron or whatever charged particle has to be changing, otherwise it wouldn't produce a changing magnetic field and a changing electric field, right? It would produce a constant electric and magnetic field. We need a changing electric and magnetic field. So you need that charged particle that's changing in speed. Okay, so what I was looking at it from the aspect of the electric and magnetic field changing as opposed to the charged particle changing in speed. But that's okay. Okay? I like your answer still. It's just different than what I was thinking, that's all. Why is it critical that the electric and magnetic field have to be changing? Josh got us to the point where we have a changing electric and magnetic field. Now we're there. Why do we have to have a changing electric and magnetic field? Yeah, if it's a constant electric field, well, that's great. A constant magnetic field, great. But it doesn't generate another magnetic and electric field, and another electric and magnetic field, and another magnetic and electric field, and so on. It doesn't move. It's not this self-sustaining, propagating thing if you don't have the concept of changing in there. You can't make the magnetic field from the electric field if it's not changing. Next question we need to go over is number 9. What properties need to be considered when choosing the material to build an antenna for a radio receiver? to be honest, when I saw this question yesterday, as people were asking me about this, I kind of thought in my mind, what properties? There's one property that's real important here. There's only one that I really think is critical here. What property needs to be considered when choosing the material to build an antenna for a radio receiver? There's lots of things you need to consider, right? Like size of the antenna, okay, depending upon the wavelength of the EMR you're trying to detect and so on. Okay, we're not going to get into that. Okay? There's one property based on the material of the antenna that you really got to consider here, though. Yep. Conductivity, right? What do you want? A good conductor or a bad conductor? Right. The better the conductor, the better. So conductivity is the answer to number 9. And finally, number 10. If the magnetic field lines held within a closed path are constant and unchanging, will there be an electric field along the closed path? In other words, will that magnetic field generate the electric field if the magnetic field lines are constant and unchanging? It's a simple yes or no answer to the first part of it, at least. What is it? No. Okay, no. And what's the explanation to that simple one-word answer? Electric fields don't generate magnetic fields. Magnetic fields don't generate electric fields. In order to get an electric field from a magnetic field, the magnetic field must be changing or moving relative to a conductor. Okay? So it goes back to that other question. Which one was it? Number 7, I think it was. Why is the concept of changing so important? Okay? You need a changing magnetic field to produce an electric field. Okay? Just a plain magnetic field doesn't produce the electric field. It's got to be changing. All right? I want to take a look at 3 multiple choice questions here, and we'll do these real quickly just as a group here together. First one, 98. Gamma radiation can be produced by... Take a look at the answer. I'll give you, or all the possible answers. We'll give you about 30 seconds to come up with something there, okay? What's the answer to the question? A. Right? Gamma radiation can be produced by radioactive decay, by nuclear decay, by matter being converted to energy. Okay, let's take a look at the next one, number 100. We've got 5 different types of EMR here: television, AM radio, gamma radiation, ultraviolet, visible light. We want to rank these in order of increasing wavelength. Okay, you see something like that, listen, I think it's a good idea to circle that, right? Because that's definitely an area where we can make a mistake. How are we used to ranking them? Decreasing wavelength, right? Increasing frequency, decreasing wavelength. So what you want to do in this question is look at them backwards, right? Gamma rays, X-rays, and so on and so on and so on. See if you can come up with an answer for this one in the next 30 seconds or so, and then we'll go over it. What's our answer to the question here, guys? A, B, C, or D? C. And it looks like consensus seems to be C. Let's go through these, okay, and determine why it's C. We're increasing wavelength, so we're decreasing frequency. My suggestion, whenever we have a question like this, just write down the spectrum as we learned it. Okay, we've got radio waves, we've got microwaves, infrared, we've got visible light, we've got ultraviolet, we've got X-rays, and we've got gamma rays. Memorize the order of those 7 in terms of increasing frequency, and then read them backwards. Gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. That's the way that we got to do this here, okay? So, which one matches up here? Well, we know we're going to start with gamma rays, so it's going to be either A or C, right? Because that's going to be the highest frequency, the lowest wavelength. Wait a second. In A, the next one is television, which is a type of radio wave, okay? And then in C, we've got ultraviolet. Which one has the next lowest wavelength or the next highest frequency? Is it going to be ultraviolet, or is it going to be some type of radio wave? Ultraviolet. So the answer is C, yeah. Now, how do we distinguish between 1 and 2? Which one has the higher frequency or the higher wavelength? We talked about radio waves, right? We didn't separate AM radio waves from television radio waves, right? So how do we distinguish between those two in this question? We don't need to, right? We don't need to distinguish. You need to know that they're both types of radio waves. Now, one of them has a frequency that's higher than the other. Okay, but in the end, we didn't need to distinguish between those two for this question. In the end, what is it? Okay, one has a lower wavelength, therefore a higher frequency than 2. So if we were to distinguish here, within here, we'd have our AM radio waves with a lower frequency, and we'd have our television with a higher frequency. Okay? Although you didn't need to know that. All right, one more multiple choice question that I want you to do here. Or a numeric response question, I should say, that I want you to do. Question 102, we'll give you 30 seconds to do that one, and then we'll go over it as a class here. What's the answer to this one? 3214, how many people agree with that? Oh, 3124, now we're getting some disagreement there. 3124? Okay, let's take a look here. Movement of the let's not even look at what we see down here, gamma rays, visible light, and so on. Let's look at 3124. 3124, thank you. Listen, if you ever write 3123 in one like this, you can guarantee that you've just got that wrong. You can't pick one of them twice. Okay. You know what I kind of laugh at every once in a while is I get an answer on a multiple choice test, and people, you know, bubble in B and D, and then they write a little note that says it could be either one. It's like, no, it couldn't. It couldn't be either one. It's either B or D. The machine that marks it on the diploma exam can't read your little note that says it could be either one. Okay, the machine on the diploma exam just marks it wrong because you pick two answers. At least I assume it marks it wrong if you pick two answers. If it doesn't, then we should all just circle in A, B, C, D for all of them. And somebody try that, hey? Somebody try that and see what happens. No, you shouldn't. You probably shouldn't try that. Yeah, we probably shouldn't try that. Not even you, Dallin. So let's forget about this down here for a second. Let's just look up here and see what the source of each of these are. See if we can identify that without even looking at the possibilities here. Movement of outer electrons to lower orbitals. That's a transition of electrons, right? A transition of electrons produces what? Well, we know that it can produce infrared, visible light, or ultraviolet. It can produce all those three. Deceleration of high-speed electrons. That's going to be X-rays. Decay of radioactive nuclei. That's going to be gamma rays. This one's a little bit odd. Rotation of an armature in a generator. Well, when you produce a generator, when you have a generator, it produces an AC current, an alternating current, an oscillating current. Okay, so what's that going to produce? Radio waves, right? Radio waves, microwaves, probably going to be radio waves, right? Okay, you got a generator, it's probably not going to make microwaves. So let's see if we can match this up here now. Gamma rays are going to be the third one. Okay, that's good. Visible light is going to be the first one. That's good. X-rays is going to be the second one. That's good. Extremely low frequency waves. I don't like that at all. I don't like that terminology at all. Okay. There is no real such electromagnetic wave as an AC wave. There's an AC current that generates radio waves, but the wave is just a really, really low frequency radio wave that's produced by an AC current, an alternating current. But in the end, didn't really matter because we knew that one had to be number 4 anyways, regardless of the terminology there, okay, because of the other ones, 3, 1, 2. All right? All right, we got a little bit more homework. Worksheet number 14, worksheet number 15. The answers to all of those are up now except number 5. I didn't put the answer to number 5 up there because there's a little bit of ambiguity in the wording of question number 5, and I want to go over that one regardless. Okay, there's a couple answers that I'd take there depending upon how you interpreted the wording of the question. So don't pay any attention to number 5 right now, just look at the rest of them, and then we'll pick which ones we need to go over in addition to number 5, okay? Anything we need to go over here on worksheet 14 or 15 besides question number 5? Which, of course, we're going to go over anyways. Any others? No? Well, do you want to go over one Nicholson question, or you guys feel confident with that? You good? I'm sorry? All right. Yeah. On 14? Yep. So we'll go over number 3 on worksheet number 14, and we'll go over number 5 on worksheet number 15. We're going to take a look at question number 3 now. It says, what is the frequency of rotation of a 6-sided mirror? That's a big deal, right? The fact that it's 6-sided as opposed to an 8-sided mirror. We're used to the 6-sided mirror here, sorry, to the 8-sided mirror. Okay, whenever we see something that's different than the regular 8 sides of the mirror, it's probably a good idea to draw attention to that by circling it. It's a 6-sided mirror. The hills are 30 kilometers apart. Also, a distance that we're not used to seeing. Usually it's 35 kilometers. Okay? 30 is okay, but it's a little bit different. Speed of light is found to be 3.10 times 10 to the 8 meters per second. We want to find the frequency of rotation. Well, we know that we've got 2 equations that we're always going to write down and we're always going to use when we're solving these problems. V equals d over t, t equals 1 over f. Little t stands for what? It's a time, yeah, but the time specifically for 1/6 of a revolution. Not 1/8 this time, but 1/6 of a revolution. Big T stands for the time for 1 revolution. Okay, I was walking around yesterday, I can't remember whether it was this class or the other class, and I saw somebody say V equals D over T, T equals 1 over F. That's great, but they wrote it down like this, V equals D over T. Okay? And you're in physics 20, a lot of times it's not going to matter, right? Even though time isn't big T, it's little t, you're still going to get the right answer most times in physics 20 if you write it down as a big T. Here you might not, because here you're going to start mixing up big T with little t. Okay? They're 2 different things. So we don't want to mix up the terminology and call them both big T and then end up mixing up which one is which. Okay, what do we got here? We have the speed is 3.10 times 10 to the 8 meters per second. Okay, we know the distance is what? 30 kilometers? Well, we got to convert it to meters, right? So it's 30,000 meters. We'll plug that in. Somebody said it? 60,000 meters. We got to double that distance. Now be careful. If they give you the return distance, and that wouldn't happen very often, but read carefully. If they give you the distance there and back, well, you're not going to double it. Don't automatically double it. Okay, read the question and see if you've got the distance one way or the return distance. All right, I told you guys that when you solve for t, it's never going to be the t you want. We're solving for the time for 1/6 of revolution here, but that's not the one we want. We want the time for 1 complete revolution. What is the time for 1/6 of revolution here? Okay, 1.935 times 10 to the minus 4 seconds. If you're dealing with a mirror that has either 8 sides or close to 8 sides, in a distance that's either 35 kilometers or close to 35 kilometers, you're going to get a time that's 10 to the minus 4 seconds. Okay, what the base is, you know, all bets are off on that. But the exponent will be 10 to the minus 4. So if you're dealing with numbers that are close to what we're used to dealing with, okay, then you're going to always get that 10 to the minus 4. And you can always use that as a kind of a little check, right, if you remember that, just to see if you're on the right track or not. All right, that's not what we want. We want the time for 1 revolution. So what do? Let's multiply it by 6. And what do we get then? 0.00116 seconds. F is equal to 1 over big T now, so it's 1 over 0.00116 seconds. Solve for frequency there, it works out to be 861 hertz. If you're dealing with numbers that we're used to dealing with, the common numbers, right? 8 sides are close to that, 35 kilometers are close to that. You're also going to get a frequency that is in the range of 10 to the 2 hertz. Okay, it could be 500 or 600 or 900, but it's not going to be 1400. Okay, or it's not going to be 37. Now, it is possible to get a frequency that's much higher or much lower, but if you do, okay, then these 2 numbers have got to be dramatically different than what we're used to seeing. So not 30 kilometers, but 6 kilometers. Okay, not 6 sides, but 17 sides or something like that. Okay, let's take a look at number 5 now as well on worksheet number 15. The issue with this one was just how it's worded. It says a radio wave of frequency 3.00 times 10 to the 8 hertz travels from ground level a distance of 50 meters reflects off of the metal roof at an angle of 30 degrees and returns to ground level. How long does it take? And what's the wavelength? No, if it reflects off of it at 30 degrees, okay, it reflects off at 30 degrees. Yeah, I see what you're saying, but it wouldn't be 30 degrees between the two because then it's, no, it's not reflecting off at 30 degrees. It would be reflecting off at 15 degrees there, right? It's reflecting off of this top metal roof at the same angle that it struck that metal roof at, which would be 30 degrees. You know what? Even that wording, Tanner, isn't really fair at this point. Later today, we're going to actually talk about the law of reflection, which makes it more understandable there that would be 30 degrees. But there's a number of things about this question that just aren't great in terms of the wording, at least at this point. All right. It says it travels from ground level a distance of 50 meters, reflects off of the metal roof, an angle of 30 degrees, and returns to ground level. What I meant this question to be, I meant this to be 50 meters. I meant that to be 50 meters, which would mean you'd have to calculate using the sine function. You'd have to calculate this side and this side, add them together to get the distance, and then use v is equal to d over t in order to find the time. Right? The problem is that's not really the way the question's worded. That's what I meant it to be, but the question is worded as it travels 50 meters and then travels 50 meters back down. What's the distance in that case? You don't have to calculate anything with the sine function there. It's going to be 100 meters. So it all depends upon how you interpreted the question. The way that I actually wrote it out when I made the question, or the way that I meant it to be written out. Okay. If you did it the way that it's literally written, you would have gotten a time of 3.59 times 10 to the negative 7 seconds. No, sorry. If you did it the way that I meant it to be, this is what you would have gotten. If you did it the way that it was actually written, you would have gotten 3.33, I believe, times 10 to the minus 7 seconds. The wavelength, any way you look at it, the wavelength is going to be 1 meter. Because it's 3 times 10 to the 8 divided by 3 times 10 to the 8. Right? Does that make sense, guys? How many people did it this way, making this 50 meters? Okay, how many people did it this way, making this 50 meters? Okay, I can't argue with either one of those because, say, the wording of the question wasn't great. So, your homework for tonight, page 652. You already saw this earlier today, but I want you to write this down. Make sure you get it done. Page 652. Number 1 to 2, and 5 to 11. We're going to have ourselves a little quiz tomorrow as well, not on the Michelson experiment, just on introductory electromagnetic radiation stuff. So the idea of accelerating charges, the idea of electric fields and magnetic fields changing and so on. Basically the stuff that the check and reflect questions was on, not the stuff that the worksheets were. Does that make sense? We'll have ourselves a quiz early next week on the Michelson experiment, okay? Just one simple question on the Michelson experiment. All right, Tanner, we're going to look at the law of reflection now, which is going to go back to your issue with that question, the difference between the 15 degrees and the 30 degrees here, and hopefully make that a little bit clearer. All of you have played pool before, billiards before, right? Hit a pool ball against the bumper, you know which way it's going to reflect off. Okay, you don't need to know anything about physics, or at least formal physics, to know that when you hit the pool ball against the bumper, it's going to reflect off at the same angle that it struck it at. That works with pool balls, but it also works with waves, and it also works with electromagnetic radiation, including visible light. The angle of incidence, the angle that it strikes it, is equal to the angle of reflection, the angle that it reflects off at. We call that the law of reflection. Now, that angle is always measured from what we call a normal line. In physics, the word normal means 90 degrees. Physics 20, we talked about normal force quite often, right? The normal force was the force of the ground pushing up. at 90 degrees. Or the force of the track, or the force of the seat, or the force of whatever it was pushing up on you at 90 degrees. Normal means 90 degrees. The normal line is a line that's drawn at 90 degrees to the reflection surface. And we always measure the angle of incidence, and the angle of reflection from that normal line. The law of reflection simply says that theta I is equal to theta R. The angle of incidence equals the angle of reflection. Well, that's easy enough, right? Intuitively, we knew that. We might not have known that we had to measure it from a normal line. Okay, we might have thought that we, measure like this and so on, but at some level, we knew where it was going to bounce off at, whether we're talking about pool balls or whether we're talking about flashlights, bouncing off of a mirror. Let's do the first question here right now together. That's a ridiculously easy question, I think. Second one, a little bit tougher. First one, we got a beam of light here that's striking a mirror at 48 degrees. It's going to bounce off over here somewhere. What's the angle of reflection that it's going to bounce off at? 48 degrees. Right? We got to get that one. This one's a little bit tougher. Let me make this angle 90 right here. That simplifies it a little bit. We want to know the angle of reflection off of the second mirror. Strikes the first one at 55 degrees. What angle does it bounce off the first one at? 55 degrees. All right. If it bounces off the first one at 55 degrees, what angle does it strike the second one at? What is it? 55 degrees? No. It's going to be 35 degrees. 35 degrees. Keep subtracting 10, you'll get it sooner or later, right? How do we know that's 35 degrees? Well, we know that this normal line and this normal line have to be at 90 degrees to each other because the reflecting surfaces are at 90 degrees to each other. If that's 90 and that's 55, 55 plus 90 is 145. 145 plus 35 equals 180. And all the angles inside a triangle have to be 180 degrees. Okay, so it bounces off of the first one at 55. It strikes the second one at 35. It's going to bounce off the second one at what angle? 35 degrees. So the answer we're looking for there is 35 degrees. The angle of reflection off of the second mirror is 35 degrees. Got to use the law of reflection there. That's the easy part. We've got to use a little bit of geometry there as well in order to find our angles. Okay? And we got to remember some of those things that we learned in Math 7 or whatever it was. Like the sum of the angles inside a triangle is always 180. Oh my goodness, what's this? Don't worry about the words here right now, okay? We'll give you a chance to write those later on, and you can even summarize them in your own words if you want to shorten it. What I want to do right now is focus on a diagram that's not anywhere close to complete right now. This is an object in front of a plain flat mirror. This might have been you this morning when you looked in the mirror and combed your hair or brushed your teeth. This is the object. This is the mirror. When you look in that mirror, you see an image of yourself in that mirror. You see yourself. But what does that image look like? Well, we know that it looks like you, right? We know that it's the same size and so on. So you got to look into the mirror to see it. You can't look on the wall behind you and see an image projected from the mirror to the wall behind you and so on. We know the characteristics of that image. But why do we get the characteristics of that image like that? You look into a mirror at a fun house, you don't look the same as you do into a plain flat mirror in the bathroom. Why not? Now, let's take a look at the simple plain flat mirror first, and then over the next day or two, we'll start taking a look at the images that you're going to see on curved mirrors, like the mirrors in fun houses or the mirrors, the convex mirrors in the convenience stores or whatever the case may be. What images are we going to see with all these different shaped mirrors? All right, well, the first thing that I want to do here is draw a ray of light from the top of the object. There's millions of rays of light coming from this object. When you stand in front of the mirror and you have the light on, the light on, the overhead light on, there's millions of rays of light that reflect off of you and therefore reflect off of you and hit the mirror and reflect off of the mirror. We don't need to look at all of them. We need to look at 4 of them here. We're going to look at a ray of light that reflects off of the top of you, your head, the top of your head. and the one that goes straight to the mirror. Now, we know that there's going to be one that reflects off at the top of you and goes up here and down here and so on. We don't really care about those ones right now. We want to look at the ray of light that reflects perpendicular to the mirror, because there is one that reflects perpendicular to the mirror. What happens to that ray of light when it hits the mirror? It's going to come straight back, right? It reflects off the top of your head, perpendicular to the mirror, hits the mirror, and then comes straight back. Let's look at another one now that reflects off of the top of the mirror, or sorry, off the top of your head. Maybe it reflects down like this. There's another one that reflects down like this and so on, but we don't really care about that one right now. We're focusing on just this one. Where is it going to reflect? Down here, right? Somewhere around there, right? So there's two rays of light that we've looked at so far. One that reflects straight back and then one that reflects down at an angle. If we extend the reflected portion of those rays, if we extend this backwards and if we extend this one back, the point where those two reflections intersect is where the top of the image is formed. So in other words, that's where you're going to see the top of your head in the mirror. The rays of light that came from the top of your head, the reflections of those rays intersect where you see the image of the top of your head in the mirror. Now, let's look at the bottom ones. I'm just going to draw these out by hand because I want you to see a different color here. First ray reflects off of your feet, parallel to the principal axis, goes straight back. Second ray, we're going to draw up here somewhere. It's going to reflect something like this. Let's extend those back. Extend the first reflected ray back. Extend the second reflected ray back. Where do you see the image formed of your feet? Below your head, right? It only makes sense, right? There's the image of your feet. So the reflected rays coming from your head intersect where you see the image of your head. The reflected rays coming from your feet intersect where you see the image of your feet. This is where you see the image. Now, what's kind of neat about this image, what's kind of intuitive about this image, is that it's the same size, right? You look in the mirror and see yourself, and it's the same size, right? We know that, right? You don't look tiny when you look into a plain flat mirror. You do look tiny when you look into some mirrors, okay, but not a flat mirror. We know that you're right side up. You don't look upside down when you look into that mirror. Some mirrors you do. You look into some mirrors, you're going to be flipped over, but not a plain flat mirror. Okay, intuitively, we know that you're going to be same size, right side up. That's two of the characteristics. Same size versus, in some mirrors, bigger or smaller. You're going to be upright, right side up, as opposed to in some mirrors, you're going to look upside down. The third characteristic, this is the one that might not be quite so intuitive. There's two types of images that can form here. A real image or a virtual image. This is what we call a virtual image versus a real image. A virtual image is an image where you must look into the mirror in order to see. A real image is an image that you can look at the mirror in order to see, but you don't have to. It can be projected onto a screen. Right now, the image formed by the lens in this projector is a real image because it's being projected onto the screen on the board. Okay, the image formed on the back of your eye, the retina, is a real image because it's being projected onto the retina. When you take a lens or a mirror and you project that image onto something, that's a real image. When you can't do that, when you can't project it onto something, that's a virtual image. Now, you stand in front of the mirror, you can see the image in the mirror, but you have to physically look into the mirror to see it. You can't project that image under any circumstances onto the wall behind you. Doesn't matter where you stand or how you move the mirror back and forth or turn it around, you can't put a picture of yourself on the wall by that mirror. not with a plain flat mirror. It always produces a virtual image. Does that make sense? Well, how do we know that this is a virtual image? How do we know from this diagram that this image can't be projected onto a screen? We get dotted lines intersecting. If solid lines intersect, then we've got a real image. If dotted lines intersect to produce our image, we've got a virtual image. That means we cannot project it onto a screen. Okay, we're going to see lots of cases tomorrow where you can project it onto a screen, where you could physically take a mirror, okay, stand in front of the mirror, and project that image from the mirror onto a piece of paper or project it onto the wall. Okay, but in this one, in a plain flat mirror, you can't do that. Okay, all these first two things, these first two little paragraphs or bullets say basically is the lines that we drew. Okay, so summarize, write down what you need to write down. And then we've extended that here to say, look, this is where the image is, where the two dotted lines intersect. How we get the image. Okay, so write down what you need to write down about that. Or don't necessarily need to write down literally every word about that, okay? Here's where we're going to pick it up tomorrow with curved mirrors. I'll tell you what these curved mirrors are, the types of them, what they look like today, and then tomorrow we'll start drawing some ray diagrams to predict what the images are going to look like. The ray diagrams aren't any harder than what we just drew. In fact, in many cases, they're easier than what we just drew for curved mirrors. But the difference here is that the image formed on a curved mirror is different depending upon where the object is, depending upon where you're standing. For a plain flat mirror, it doesn't matter where you stand, the image is going to be same size, it's going to be right side up, and it's going to be virtual. So we're going to have to draw lots of ray diagrams tomorrow for this. Before you pack up, I would just really quickly tell you what each of these mirrors are. A converging mirror, a concave mirror, is a mirror that's thinner in the middle than it is at the edges. So if we're looking at it as a cross section, the mirror would look something like this, right? Thinner in the middle than it is at the edges. It's caved in. That's what we call it, cave in, or concave. We also call it converging because rays of light converge together. Rays of light that strike it, they converge. They come together, they intersect. As opposed to a diverging mirror, or a convex mirror that's thicker in the middle than it is at the edges. And that's like that security mirror that you sometimes see in the corner of stores. You guys have seen these a million times before, right? Diverging, we call a convex mirror a diverging mirror because the rays of light that strike that don't converge down here, but rather they diverge away. Like this. They go away from each other. All right? So that's where we'll leave it today. Tomorrow, again, we'll draw some ray diagrams for this. We'll move a little bit further with this, and we'll see some of the characteristics of the images produced on these types of mirrors. All right? That's it for today. Don't forget your homework for tomorrow, page 652. Number 1 to 2 and 5 to 11. And remember, you got a little quiz tomorrow as well. Not on the Nicholson stuff, but on all that other stuff that you had your homework on last night. Okay? That's it for today, guys.